Alrighty, hi everyone. We might make a start for the seminar for today. So today we're really lucky to be joined by Gideon Billings, and he's a research fellow at the ACFR, the Australian Centre for Robotics, based at the University of Sydney. And today he's going to be talking to us on the topic autonomous underwater systems for the exploration of extreme ocean environments. So please join me in making Gideon feel really welcome.
Great, thank you so much, Scarlett. So yeah, it's a pleasure to be here, and yeah, feel privileged to be able to give this talk to you guys. So yeah, a little bit more about myself. I completed my PhD at the University of Michigan in early 2022. Took a little stint after that to backpack through South America before joining the Woods Hole Oceanographic Institute for about a 5-month postdoc while I was waiting for my visa to come through for joining the ACFR. So currently a research fellow under Stephen Williams with Marine Robotics Group here, and loving the work that I'm able to do with these guys. So yeah, I've worked on many different underwater systems throughout my research, but for me, a really strong motivator has always been to explore the unknown, which you can probably, tell that I binged Star Trek growing up through high school. So, kind of understanding more about our universe, more about what we don't know, building systems that can get us into those places. So it wasn't a hard decision for me when the opportunity came up to do a PhD funded by NASA on underwater robotics with applications towards future space exploration missions. And that choice has since led to some really incredible experiences, collaborations, and some challenging research problems. So much of my research under this project and following projects has been around kind of autonomous sampling and intervention with remotely operated vehicles. Traditionally, and still, those vehicles tend to require pilots to directly control their actions. So a common goal throughout my research has been to increase the capacity for autonomy in underwater systems, with the goal that this could enable the exploration of alien ocean worlds, such as Europa and Enceladus, also enable operations in remote and difficult to access places within our own world, like deep under ice shelves. And also these same automation processes can enable scientists to directly drive the intervention and sampling processes of vehicles rather than requiring an expert pilot in the loop to kind of facilitate what the scientists' goals are. So this is a very kind of typical sample of what it looks like to collect an underwater, a sample with a tool. So it is one of the most basic samples you can collect in the ocean. It's kind of a push core, sediment push core, and scientists will take that back and study what's in the sediment. But even this very simple task, you can see there's a lot of challenges for an automated robotic system. The dexterity required in the manipulator to kind of pick up the tool, place it in the location of interest, and put it back in a very cluttered kind of workspace. And also the act of sampling and interacting with the environment can kick up a lot of sediment and cause perceptual degradation that challenges automated systems. Environments of interest are also often quite challenging by their nature. So these are unknown environments going in. We don't have prior maps or knowledge of many of these environments. So we don't know what to expect. And often they can be structurally complex or visually complex, like this example here, where there's lots of bubbles coming off of this thermal vent. It's quite difficult from a perception perspective. So there's many risks to deploying underwater robots when you think of them compared to terrestrial systems. So first you have the risk of environmental disturbance. So that could be, disturbing a delicate environment, but also the risk that disturbing the environment degrades your operational environment and makes it challenging to even operate. There's the risk of vehicle survivability. If something goes wrong, the vehicle can end up at the bottom of the deep ocean with no real way to recover, or imploded and then no possibility of recovery. And then there's also risk of mission completion. So, if things go wrong, you may not complete your goals, your scientific goals for the mission, And many of these scientific expeditions are years in the planning, very fixed ship time available, very expensive. And so if you don't get what you need out of it, it's a huge loss. And compared to terrestrial systems, hardware underwater is very expensive to build. Operations are much more expensive. The observation of your system while it's deployed is very limited. You can't just look under the water and see what your system's doing. Again, hardware is prone to failure. Water is corrosive, at least marine water is, and high pressured environments. So it's not if things will fail, it's when things will fail. Our vehicles on field ops are opened on the bench a lot more than we'd like them to be. And also the ability to intervene if something goes wrong with these systems is limited. You can't just throw on your dive suit and jump in the water to rescue a vehicle that's, hundreds of meters or thousands of meters below the surface. So this is what it looks like to operate a typical large ROV. You have a control station that's in some ways analogous to a space operations center. With lots of screens, control panels, multiple pilots controlling the system. Typically, you'll have one pilot in charge of driving the vehicle and kind of maintaining contextual awareness, and you have another pilot who's in charge of doing manipulator control or intervention tasks, and they kind of help each other. And so these systems tend to be tethered to a surface ship and directly driven by pilots, maintaining a high level of safety for these systems that have to interact with the environment. Autonomous underwater vehicles, on the other hand, they operate without a pilot in control, but they generally run on these very carefully pre-scripted mission plans that have hard constraints, operational constraints. And if the system deviates outside of those constraints, then the system's going to generate an abort and generally try to surface, and then you recover it and evaluate what went wrong with the system. So that kind of leads to this general golden rule within marine robotics that first and foremost, number of deployments should equal number of recoveries. And that's kind of what we emphasize when we do field deployed robots. So when you think of the design of underwater systems, they tend to be designed within application-centric kind of approach, where vehicles are highly specialized for what their intention is. When you break that criteria down, you tend to arrive at two very kind of distinct types of systems. So autonomous underwater vehicles, which tend to be hydrodynamically efficient, designed for doing survey, and then these intervention systems that are designed to operate by a tether from a ship with pilots in control of them. However, if we're designing vehicles for exploration of remote or extreme environments, it requires a bit more of a hybrid approach, because you cannot rely on a tethered vehicle to go and collect you samples very far under ice or on an alien world. And you also cannot rely on very strict, rigid, mission-planned regimes to operate if something goes wrong in an environment where you cannot surface or recover. So this leads me to kind of the project that I alluded to that started all of my marine robotics research, which was this NASA-funded P-STAR project that I was offered to join at the beginning of my PhD. This was a collaboration between my home University of Michigan, the ACFR, which is how I was first introduced to the marine group here, Woods Hole Oceanographic Institute, and MIT. And so this P-STAR program funds terrestrial-based research towards developing technologies that can enable future space exploration missions. So NASA is interested in this because one of their primary goals is to search for life outside of the bounds of our Earth. In our deep oceans, we have these thermal vent systems, which I've alluded to before, and these vent systems are driven by geothermal processes in the core of the Earth, which cause chemical vapor, hot vapor, to come out of these vents in the deep ocean. There's a kind of bacteria that lives on these vents that was only discovered within the last century. And they, instead of relying on photosynthesis, which most of the life we're familiar with does, they can fixate carbon dioxide directly from these vent systems into energy. So it's through a process called chemosynthesis. And then those bacteria in turn support a whole pyramid of life that thrive in the deep ocean where no light can penetrate. NASA is interested in this because we have, some of you might be aware, a couple ice moons within our solar system around Jupiter and Saturn. And there's some evidence that there could be liquid oceans under the surface ice crust of these moons. If that's the case, it indicates that geothermal processes are operating in the core of those moons. And if there's geothermal processes, then there could be hydrothermal venting that could also have the ingredients for chemosynthetic life. So that was why NASA was funding this project. It was a very large-scale project that involved multi-vehicle coordination, where we had a surface ship that kind of acted like an initial satellite flyby, doing surveys. In the case of a ship, it was with sonar. In the case of satellite, it would be other types of sensors. Do an initial survey of an environment you're interested in exploring. We used autonomous underwater gliders that would then go and with other sensors and explore areas of interest within your bathymetric maps, kind of initially constructed from the ships. So that's kind of analogous to a low Earth orbiter that could go through and do some more detailed surveys. And then a remotely operated vehicle that acted kind of like a lander, where you would pick your specific sites of interest. That remotely operated vehicle would then go and explore and determine, is there actually thermal venting at that site? If so, collect some samples and do some science. So this is a graphic from one of the field expeditions as part of that project. This was off the continental shelf break in Costa Rica. So this shows some of the bathymetry that was collected by the ship. And then there was some initial thermal venting evidence within the sonar data of the ship. So then a glider, which you can't see very well, it's kind of that pink path. A glider was sent down with a sonar to verify thermal venting. So essentially it's looking for the bubbles coming off the vent, which are those bubble plumes that you see. And then based on the detection of those, a plan was made for an ROV, which was the track in yellow, to go down, visit those sites and collect samples where there was thermal venting. So my work as part of this project was really focused on increasing the autonomy of an ROV system as an analog to a lander. In an environment like Europa and Enceladus, there is no way to do any kind of direct control of the vehicle. It's going to be on its own. So it needs full autonomy capability. So I worked largely through my PhD with this kind of specialized ROV system called NIRID under ice. Traditional ROVs use a tether for both power and communication. So they're tethered to a ship with a very thick tether. And then to minimize the dynamic loading between the ship and the vehicle from the tether, the ship has to station keep directly over the vehicle. So this limits traditional ROVs, large ROVs, to operating in open ocean areas where ships can access. The NUI vehicle is a hybrid ROV that carries all its power on board. And instead of a large tether, it only has a hair-thin fiber optic tether that spools out between the ship and the vehicle and just supplies communication. So it can still be teleoperated, but because it's a hair-thin tether, it can spool out for kilometers and the ship can stay in place and the vehicle can move away from the ship. The kind of design inspiration for this vehicle was to access under ice shelves and start to be able to kind of get under there and collect samples and do some intervention. So this vehicle can operate in a AUV mode. So if the tether breaks, it can home its way back to the ship. And there's also, you can do some level of like wireless communication through optical and acoustic modems. So this was a vehicle that I worked with mostly. It was designed and built at Woods Hole Oceanographic Institute, and it's kind of a one-of-a-kind system. All right, so a massive challenge for automating underwater intervention systems is the perception problem, which is my particular interest. The image formation process in underwater environments is nonlinear. It's subject to many degrading imaging effects. And again, operating intervention systems in close range to the environment also risks environmental disturbance and degrading your scene. Within the scope of this project, I worked on several different vision problems. So I'll kind of briefly talk about some. But an idea I leveraged heavily within my work is that your workspace can kind of be divided for an intervention vehicle into two perceptual environments. So you have your unknown environment, which is generally unstructured, uncontrolled, and highly uncertain, in an unexplored and new location. And then you have your known environment, which exists within your structured and controlled workspace of the vehicle. And within that controlled environment, we can also have prior models of things like tools and your vehicle itself. And then a second idea I explored in my work is the use of manipulator-mounted wide field of view fisheye cameras. So wide field of view can enable dynamic viewpoint acquisition without needing to move the vehicle around, which for large ROVs was a big advantage because the thrusters on large ROVs, if you try to lift up and move location, they completely degrade the whole scene. You have to wait minutes for the sediment to settle down. And also that manipulator-mounted camera proved to be advantageous for detecting and grasping tools within the confined space of your workspace, where vehicle fixed mounted cameras don't see your workspace very well. So just very briefly, I'll go over a few of the problems I worked on within this context. So one of the first things I worked on was an object pose estimation method that was specially adapted to underwater. And so I called this SiloNet. So this method would predict silhouettes. So essentially, they're kind of like a segmentation mask of the object. But then if the object was occluded, it would fill in the silhouette to be the full silhouette of the object in its current pose. And then that could be used to estimate from the silhouette the orientation of the object. So this proved to perform very well compared to methods at the time. And it ran on top of an object detection method that could take a region of interest and a class ID as input. And this method was inspired by having known prior models of your tools within your workspace that you were trying to detect and manipulate. So then I took that work and I extended it to work on fisheye cameras for kind of cameras mounted on a manipulator with underwater imagery. So one of the challenges with fisheye imagery is this large distortion space. So if you take an object and translate it without rotating it, and then take a region of interest crop around that object, the apparent rotation is going to look very, very different depending on how you translate it. So this was a challenge to how traditional pose estimation methods were set up, where they would try to predict directly the orientation relative to the camera frame and the translation. So in this method, I kind of used the mnemonic projection, which is an old mapping used for maps, navigation maps, to map onto a sphere what I called an apparent viewpoint of the object. And then I could do your object detection and pose estimation within the frame of that apparent viewpoint, and then do an inverse projection back to the fisheye frame to do your camera relative pose and orientation. So I did some analysis of different ways of using that mnemonic mapping operator within a neural network architecture, found an approach that kind of performed the best. And then as part of this work on the Costa Rica shelf break, I collected a data set. Nowadays, it would be considered very small scale, but it was enough to kind of train the method on underwater fisheye data and evaluate it and show that it got reasonable performance for being able to grasp and manipulate objects. That was one of the problems that I worked on during my PhD. Another problem that I looked at was how you can co-register cameras mounted on the vehicle with the camera mounted on the manipulator. So you have on the vehicle, we had perspective kind of regular stereo for doing good depth maps, but a limited viewpoint and strong features. And then the fisheye camera on the manipulator, which is a much different camera model. So I looked at implementing an adaptation of Warp Slam 2. And I modified it so that it could handle hybrid keyframes, which included synchronized fisheye camera from the manipulator plus the fixed stereo camera from the vehicle. And then I adapted kind of the processes to be able to use those hybrid frames. And it allowed the fisheye camera to dynamically move relative to the stereo pair. And then this framework was adapted to leverage real-time QUT features as well, which performed much better underwater than orb. So here's just a little video snippet of that working on. So on the left is a stereo sequence from Lizard Island that we collected. So that was preliminary kind of evaluation of the method. And then on the right, it shows the mapping from a deep ocean data set where the fisheye is being registered into the stereo view. And you see on this large vehicle, the stereo is pretty much stationary. You're not moving the vehicle around. But the fisheye is able to kind of extend the view and see around the occluded spaces of the scene where the stereo can't. So that was a couple things that I worked on the perception side. And then on the hardware side at the same time, I worked on building an autonomy framework that could seamlessly integrate with the teleoperated system that the pilots use. So this framework could enable an operator to assign high-level pick-and-place style tasks, and then the execution of the task was broken down into sequences of motions that could be visualized to the pilot. They could override them, verify that they were safe. And it reduced risk of testing and deploying this autonomy stack on a very, very expensive vehicle asset. So using this, this was one of the, anyways, this was the very first basic thing that I did, a simulation, a pick and place pipeline, but part of this was to build a pipeline that was specialized to underwater tools and also kept very transparent the things that a pilot would want to know was happening in an underwater system. So this was a preliminary kind of in simulation, leveraging MoveIt to build this system to do push core sampling was the first task that we tried to implement. This was the first demonstration of the full pick and place pipeline working in a lab setup. It just had a very simple setup, but this was also all done on a hydraulic manipulator, which this manipulator was built in the 70s, not built for automation at all. So there was a lot of control challenges around getting the accuracy needed to actually automate this thing. So then in 2019, I participated in a field expedition where we used this vehicle to explore the active submarine volcano Colombo, which is a volcano off of Santorini in Greece. And we were able to demonstrate planar-controlled biological sampling at 1,000 meters deep. So unfortunately, there was an issue, as is always the case in field work, where the manipulator slew joint, the rotation joint, was having issues, so we couldn't precisely control the manipulator, but we were still able to get published first, which was a planar controlled collection of a material sample using this slurp hose, which is kind of like a large vacuum cleaner. So there was no pilot in the loop. We were able to just press some buttons and have the manipulator collect some biological sample. So you can see here an example of the challenges of these kind of environments. The whole seafloor in the caldera is just thick bacterial mat. And anytime you try to collect a sample, it just kicks up tons of sediment, which made the visual side of things very, very challenging. We also did a very preliminary demonstration of natural language control of this system. So in collaboration with Matthew Walter, who's at Toyota Technological Institute of Chicago, we were able to demonstrate a natural language interface that allowed you to put text commands or speech commands to the autonomy system, and it could essentially reproduce any of the pick and place pipeline commands. So that was preliminary work during my PhD. Towards the end of my PhD, and then in my postdoc at Woods Hole Oceanographic Institute, we started extending this work. So a big challenge for conducting deep ocean science is that currently vehicles that are capable of operating in the deep ocean are very few, and they typically require large ships to support operations. And the cost of operating these vehicles is generally on the order of 50 grand or more per day. The berth spaces available on these ships are very limited, and you also have a very tight operational window to collect your data and samples. So this motivated expanding this autonomy framework to a system that could enable any number of both ship-based and shoreside scientists to engage with the vehicle operation in real time. So rather than just waiting on shore for the mission to be completed and seeing what samples come back, you can be actively engaged with the process of collecting those samples. So we built a networking framework around our core autonomy system, and this had a 2-server architecture where we had a field server that interfaced directly with the vehicle's autonomy framework. Vehicle ran ROS, and then that field server encoded data into a lightweight messaging library, 0MQ if you're interested, and then that was transmitted to the shore server. And then the shore server, implemented a star topology network framework that allowed any number of users to kind of dynamically connect and disconnect from the server. The shoreside system also implemented some security layers that ensured only registered users could connect and disconnect. And we also had a system that enabled dynamically assigning who is actively in control of the manipulator system at any given time. So then this system we took in 2021 and demonstrated in a field expedition off of the west coast of the US in California. So myself, Matthew Walter, were on the ship, and then we had a team of others who were involved in building this system, Andre Daniello, Amy Fung, and Dr. Richard Camilli at Woods Hole, who was leading this work. So in 2021, we had developed both a desktop interface and a virtual reality interface into the system. Our major emphasis was on the development of this virtual reality interface, which supported both hand gesture input and also natural language commands. And then the demonstration was a multi-step collaborative sampling task where we used this device called an X-ray fluorometer, which Richard Camilli developed, and that could in real time measure the molecular composition of materials. So then in this demo, Matthew Walter initiated an automated pickup, a tool command using a spoken command. And then once the system grasped and removed the tool, Amy Fung with a VR interface was able to position it precisely where we wanted to collect the sample. And then in real time, Rich Camilli was able to look at the data coming through the XRF and give feedback on where the tool was positioned. And then we were able to finish the sampling process and recover the tool with no pilot in the loop. This was all controlled by people thousands of miles away from the system. So that was a pretty cool success. So then we took the lessons learned from that and kind of improved the virtual reality interface. And then we set up some trials at lab where we could conduct some user studies to try to evaluate and demonstrate how novice users could operate the VR interface with precision enabled by the autonomy framework. So this is just an example of that VR interface and what that looked like. So we conducted a set of user studies that involved two kind of representative tasks of things that you do with an underwater system. So one is picking up a block, putting it in a basket, just kind of like collecting a rock sample. And then the other one was taking a push core out of a quiver and trying to place it in the center of a target and then putting it back in the quiver. And we evaluated how accurately the user could position the push core on the target. We had a pool of users that included both expert pilots from the Woods Hole Oceanographic Institute, had lots of experience with controlling underwater manipulators. And then we also had a pool of novice operators who had never seen or touched an underwater manipulator before. And these were time trials. So the big takeaway from this was that under reduced frame rates, which was represented by delay or bandwidth limited communication, we found that there's an exponential increase in the expected time for both novices and pilots to complete a task as your frame rate decreases. This result was consistent with Sheridan's observation 60 years ago, where he did experiments and noted that under delayed communication, users tend to start directly teleoperating a remote system, or users who are directly teleoperating a remote system will tend to opt for making small open loop adjustments than waiting to see the response of the system before making another iterative adjustment. Whereas with the autonomy system, it's able to kind of close the loop in a delayed communication setting. So you don't need to make those iterative adjustments that lose time. We also found that both novices and pilots were more precise with their push-pull sampling than with the direct kind of joystick operated approach to manipulation, traditional approach. And I also found that my aunt could operate it very easily and with very little training. Okay, so that wraps up my discussion of that first project funded by NASA, kind of towards automating these underwater intervention systems. And we're still doing a lot of work currently building off of that work. And I'm actively involved with several projects here at the ACFR on that kind of space. So now I'm going to move towards talking about another project that I got involved with during my postdoc at the Woods Hole Oceanographic Institute. And this project was motivated for long-range exploration under ice. So currently, we don't really have good systems that can go fully under ice shelves. There are a few, but in general, you require a vehicle that has a very high range. You know, we're talking, we don't want to just go 10 kilometers or even 100 kilometers. We want to go 1,000 kilometers under ice. And there's very few systems that can do that. And generally, as your range increases, the mass of the vehicle also increases. You need more batteries, more capacity. Also, the expense tends to increase with the mass of the vehicle. So systems that are capable of long-range operation tend to be quite expensive and quite heavy and logistically complex to deploy. However, you'll notice on this graph at the bottom right, there's a set of vehicles that are not very big, but they can go super long range, and those are gliders. And if you're not familiar with gliders, gliders are a special type of autonomous vehicle that can fly essentially through the water column on wings. And so they use buoyancy drive instead of thruster drive as their primary propulsion method. So gliders can go both positive or negatively buoyant, and they're designed to go through basically, you know, traditional ones can go 1,000 meters or more in water depth, and they'll just glide in a yo kind of pattern through the water. That means that gliders only need to burn energy when they change their buoyancy at the bottom of an inflection to go positively buoyant. So these vehicles can go super far and operate for very long duration. Also, because they're so power efficient though, and they're still limited in battery capacity from their size, they tend to operate very low power sensors, and those sensors can be turned on and off. Traditionally, gliders will constrain their navigation by getting GPS fixes at the top of every yo cycle. So they'll start with a GPS fix, do one long dive through the ocean, or through the water column, come up, grab another GPS fix, and that can constrain their navigation drift. There's been more and more interest in leveraging these vehicles for long-range exploration under ice, but that kind of breaks the traditional way you operate these systems, because under ice, you can no longer surface for GPS fix. You also end up in regimes where you're depth constrained. So if you're under the keel of an ice floe, you may not have full water depth to do an efficient yo cycle. So it requires a system that can navigate accurately enough to get under the ice and back out without requiring surface fixes, and also be able to fly in narrower depth bands, depending on the keel depth of the ice. So in this project, I worked with Dr. Richard Camilli on developing this long-range underwater glider. that we modified from a stock Slocum G3 glider. So he did some work on modifying the wings and the tail of the glider so that it could fly more efficiently. He also built a custom thruster that was more efficient than your stock thrusters. So the glider was able to operate in hybrid mode, where it could seamlessly transition between using buoyancy drive or thruster drive. We built this backseat architecture system that could interface with the flight computer. So you could fly the glider as a stock system, or you could leverage this backseat architecture. And that backseat had a DVL, a mechanical scanning sonar in the nose of the vehicle, CTD, and an AHRS. So those were the key sensors that we integrated into the stock system. This graph just shows the improvement of the flight dynamics by modifying. Simple modification to the shape of the wings significantly improves the lift to drag ratio. And again, everything on gliders is about improving the efficiency and minimizing power loss. And then Richard Camilli did some analysis on the different operation modalities for gliders. So what we found is if you're in full ocean depth with low hotel load, meaning you're not operating very many sensors, just collecting sparse oceanographic data, then you're most efficient to fly with buoyancy drive, where you're yoing through the water column. However, if your depth band becomes constrained to less than 100 meters, now actively cycling your buoyancy drive becomes less efficient than just driving by thruster with neutral buoyancy. If you start operating a hotel load of sensors, say you want to collect more sensor data, like run the DVL, mechanical scanning sonar, if that operates at 15 watts, which is actually quite low for a sensor hotel load, then that depth band where you become more efficient to operate by thruster is extended to 300 meters. So gliders are most efficient when they can leverage the full ocean depth. But if you're really interested in operating in a constrained depth band, then you want to operate with this hybrid thruster modality. So based on our stock glider modifications, we ran some numbers where we kind of looked at transit mode, coastal transit mode, where you have all your sensors turned off that you don't need, just your navigation sensors running, and then survey mode, where you're running the mechanical scanning sonar and all of your sensors that you want to collect data with. And what we found is that when operating with full sensor payload, we could get a range with our glider of 1,500 kilometers in a constant depth band thruster-driven mode. And if you're operating, in transit mode in deep water, gliders just get incredible endurance. They can get a range of 14,000 kilometers and endurance of more than a year. So quite an incredible vehicle to work with. But that comes at the cost that compute is very low power. Everything is, much more challenging to implement. So this was the architecture that we developed for our backseat system to interface with the front seat. So it used a very simple raw system that implements a navigation mode and a mission controller, which can communicate to the stock computer and can update the mission parameters of the stock computer on the fly. And then I worked on implementing this DVL odometry process that could kind of dynamically profile the water column currents as the glider was on the fly. And anytime the glider got bottom lock with the DVL, it could update its odometry estimate and correct for water column currents dynamically. Because we're often starting the glider in very deep water where there's no DVL lock on the bottom. And then we're interested in flying closer to surfaces to do profiling and survey. So for operation under ice, we had funding to do some operations in the Arctic, kind of in what's called the MIZ, so the marginal ice zones of the Arctic. So one of the challenges there is we had, very little keel depth between the ice and the seafloor. And we also needed a mission architecture that could safely navigate under ice and back out. where if something happened like an abort, the glider wouldn't try to surface under the ice and potentially get stuck. So we developed this kind of backseat, front seat mission architecture that could handle abort cases under ice. And then we implemented this carrot following approach to the mission controller, where the backseat kind of ran this improved navigation stack that had a better idea of where the glider was based on this DVL odometry process. And then it would feed carrot positions based on the front seat's estimate of where the front seat should go. So again, it didn't touch the front seat stock implementation, but it kind of worked with it to fly the glider. So we spent 2 weeks in the Arctic out of northern Alaska, living on this boat with 5 other people. Had used a kitchen pot as a shower off the back of it. And we conducted some surveys with the glider under the marginal ice zone. So one of the challenges we found, which was a bit unexpected, was the amount of grounded ice at the edge of the ice shelves. So there was some very hectic icebergs that were grounded completely in 40-meter water depth. And so it was a very challenging place to even find a place where we could operate safely. So there's a lot of challenges about operating in these extreme locations. But we were able to find some locations where we could do some preliminary demonstrations with the glider system. So we were able to show that the odometry process was able to improve navigation over the stock backseat or stock flight system significantly. We were able to get about an average of 8 to 10% error over ground, which is quite good for a glider. And we also showed that the DVL odometry process accuracy was better than just running water lock based velocity or bottom lock based velocity alone from a DVL. So if you're familiar with a DVL sensor, if you're within about 40 meters of the bottom, you can get what's called bottom lock, where you're doing an absolute reference velocity relative to bottom. If you're outside of the range of the bottom, then you do what's called water lock, where you're doing velocity relative to the water column, but the water column could be moving. So we showed that our DVL ODA process could combine both of those to do the best kind of accuracy we could get. So one of the things we were doing is using the DVL to both do kind of sparse bathymetric profiling of the area where we were surveying. And then we were using the mechanical scanning sonar in the nose of the glider to do both bathymetric profiling in some missions, but also scanning for ice for other missions where we were operating under ice. So we were able to show that when the imaging sonar was configured in an upward looking sweep, we could detect and characterize chunks of ice in the water. And so that's what these kind of graphs show, where you can see the signal of the ice chunks in the sonar return. And we were even able to integrate these signals into kind of volumetric estimates of the ice cover. So this was work that Amy Fung did, who I've worked with a lot in these past projects. It was an incredibly beautiful place too, one of the most beautiful places I've ever worked. This was an image from one morning during that field work. So again, it just brings home the importance of, collecting this data, understanding these environments, and giving scientists what they need to know how to conserve, our natural world. So that kind of brings me to, the end of the 2 main things that I wanted to talk about, the 2 main projects. But I'll just talk a little bit about what we're currently doing. And so for me, this slide kind of captures a bit of my philosophy for how I think about the field robotics research that I'm doing. So I call this my subsumptive approach to perception for field robotics. So it's kind of inspired a bit by Rodney Brooks, who had this, idea of intelligence is an outcome of levels of competence in a robotic system, which, there's varying views on whether or not that's actually proved to be legitimate or not. But I think these kind of points really apply to field robotic systems. And I think of it, instead of intelligence, as autonomous capability. So for me, in my mind, field robotic systems should be situated in real time for real-time response to the environment where they're operating. And they should be embodied and grounded in the real world. And then again, autonomous capability is determined by the dynamics and interactions with the world, and you get emergence of autonomous capability through levels of competence that you develop. So how I've kind of structured my research work is these different levels of competence, where at the lowest level, I think of it as, your feature representations, your localization, your vehicle state, how you're fusing your low-level sensors. And then those enable your mid-level capabilities, where you can do dense reconstruction, semantic mapping, model priors. And then that enables your highest level, where you get your planning. You can do active viewpoint acquisition. You can detect changes in the scene. So this is kind of loosely how I think about framing the research problems that I'm working on. And whenever I'm working on one level, I think about how I can leverage the levels below it. So that leads to one of the problems that's been a big focus for the last couple of years with research that I've been doing here at the ACFR. So this is, how can you leverage your real-time kind of sparse SLAM maps that you're building for dense depth prediction? So this was something that I was thinking about in my PhD. And so the idea is that your SLAM map provides you with very strong depth priors, and that can enable improved depth map, metric depth mapping from both monocular images or even stereo images. So I had a master's student that I was co-supervising 2 years ago, and he kind of took this work and ran with it a bit. So there was some recent work on monocular depth estimation that was coming out at the time. And so he looked at how you could represent these sparse depth points as a densified representation of a depth map prior, and then how you could fuse that into a metric depth estimation network using monocular relative depth plus that sparse depth prior map. So he's able to show some really promising preliminary results. Around the same time, ZOE depth came out, which showed incredibly strong single shot performance on underwater data without any training on underwater data. And then you have the depth anything V2, which came out, and you can give it a very turbid sequence where a conventional depth estimation method would be very poor, and it can actually put out something sensible. So this inspired some work that was done over this last year with a student that I'm kind of co-supervising, Jay Zhang. And we just submitted for publication this method called SPADE. And this method is built on a monocular backbone like depth anything V2. And then it can leverage sparse feature priors, which can be from, again, stereo or VINs or any kind of SLAM process. And it can do a scaling operator on the second stage, and then have a third stage network that refines the depth prediction to do a metric depth map. And we showed that this can run at 15 frames per second on a Jetson Orin, which is the kind of device that we're running on our vehicles. So very promising results for running real time on our underwater systems. Another thing that we've been up to in lab that I've been heavily involved with is the Seeker AUV, which is a highly maneuverable AUV designed for benthic survey. And we've been working on developing this vehicle for over the last 2 years. And we've gone from prototype to having several vehicles built and having operated them all over the South Pacific. Most recently in the Solomon Islands, where I did some field work for a month. And we demonstrated with 2 vehicles doing, this is just one of the surveys that we did, a very large scale survey, doing benthic imaging, and then combining all of those imageries into a large scale photo mosaic. And this photo mosaic is about, I think it's 10,000 square meters and extends from 30 meters deep down to 120 meters deep. And this vehicle has been designed specifically for high quality imagery. So the lighting and the imagery provides very high resolution and detailed images. So one of the things with this vehicle that also kind of fits with the depth mapping work that we're doing is obstacle avoidance problems. So currently this vehicle leverages just a very simple narrow beam forward facing sonar that can kind of tell you if there's an obstacle in front of you, and it will try to go up and over the obstacle. But when you're working in very rugose and complex reef environments, overhangs and caves are a big risk. And currently it's very difficult to detect and handle that kind of environment. So what we're working on now is extending that depth mapping work to run on a vehicle like the Seeker with forward-facing camera plus scanning sonar, and leveraging that to be able to do obstacle avoidance planning and also detect caves and more complex terrain. So that's one of the problems that we're working on. There's several others, but that's kind of what I had time for today to talk about. So that, I think, brings me to the end of my talk. And yeah, hopefully there was some interesting stuff there for you.
Thanks so much, Gideon. Can we give him a round of applause? Really, really interesting talk. Do we have any questions? We've got a bit of time if anybody has a question for Gideon. I've got one to start with. So Gideon, you talked about a lot of different extreme environments, the thermal vents, the active volcanoes, and then also the Arctic. What do you think is the most challenging environment? And are there other environments that you haven't worked with that you think would be even more challenging or interesting?
Yeah, so I think of the environments that I've worked in, under ice is the most challenging, because even, you know, the active submarine volcanoes, the deep ocean, you can still have a tether to your vehicle, even in the deepest part of the ocean. And there's also human occupied submersibles that can reach those cases, you know, if you have the funding and the money to throw at it. Getting vehicles 1,000 kilometers under ice, that's very high risk. There's not a lot of humans who would want to risk going under there with a submersible. And yeah, if something goes wrong with your vehicle, it's completely inaccessible. So that's an area that I'm very interested in continuing to work on for my research. And there's a lot of interesting things on the sensing side, because it's not just like you want to go under ice and have a large standoff distance. You want to be able to go under ice and image, you know, is there algae on the bottom side? Do you need to collect samples? You want to survey what the ice kind of dynamics are doing. So that water-ice interface is really interesting to scientists to understand dynamics between ice and the ocean currents. So it's getting close to these things that are very high risk to operate around. So to me, that's super interesting. Of course, the most challenging environment to get to is going to be the extraterrestrial ones, where we're trying to sample, you know, on an ice moon. But we're still a ways off from that, I think.
Really cool. Thanks, Gideon. Any questions in the room? Yes.
Hi, Gideon. This is Dorian speaking. Thanks for the great talk so far. I just had a quick question. Actually, it's quite similar to Scarlett's, which is, given your broad experience across marine robotics, what do you see as the major technological challenge for having a fully autonomous, capable, you know, under the ice, long range exploration happening? Just in terms of like perception, high level stuff. Is it sampling and interaction? Is it scheduling, high level autonomy, that sort of thing?
Yeah. Yeah, I think if, again, there's vehicles that can go under ice that are very expensive, very large, and you know, they have every expensive sensor you can throw at it, like INS, that's, you know, very precise navigation. And you can run full, you know, imaging sonar, whatever you want. The problem is these vehicles end up being so expensive that the risk of putting them under ice is quite high, and then you tend not to operate them as risky as you'd like to get to the interesting places. So that's why there's kind of this push towards cheaper assets like gliders that are 2 orders of magnitude cheaper, or even more than some of these very expensive assets. But then you're now limited to, you know, battery capacity is highly limited. Your sensors that you can operate with are highly limited. So then it becomes, what can you do with these super low cost, well, relatively low cost but mostly low power, low rate sensors. And so it makes the problem quite challenging in that regard. So I think the navigation accuracy, especially when you are without an absolute reference frame, is one of the most challenging problems. Of course, there's other problems about like navigating around grounded ice. Like how do you even find your way through, or how do you adjust, your depth when the ice, rugosity is many tens of meters or more. So yeah, but I guess that all kind of falls under this navigation kind of problem. So yeah, I think that's where a big part of the challenge is.
Thanks, Gideon. I've got one in the chat. So Joshua asks, what sort of things were you doing during your undergrad as an electrical engineer to learn more about marine robotics?
Yeah, I actually didn't get really involved with marine robotics at all until my PhD. I was a member of the Mars Rover Club at University of Michigan for a while. And I knew I wanted to do robotic exploration of some kinds quite early on, even before university, like undergrad. But I wasn't sure whether that would be space or underwater. But the more I learned about underwater, the more I realized like underwater, you can be hands-on, you can design every part of the system, you can be involved with the hardware, the software, and the deployment, which is a little different than the pace of space robotics. So it was kind of opportunistic for me, like that this project turned up and it happened to be space and underwater. So yeah, it was something that I was definitely very fortunate to have that opportunity. But in our lab, we have a lot of undergrads and who are actively engaging with research in our lab, and we try to be very open to having students come in here at the ACFR. So we've got quite a few students now who have started, as an undergraduate project in our marine robotics lab, and then have decided to go on and do PhDs and end up being, core members of our marine group. So.
Awesome, really cool. Any other final questions before we? Oh, yep, another one from Dorian.
Again, more just thoughts on the under ice sort of situation. In terms of mapping it out and navigating, if the ice is transparent, how do you see it and avoid it? I assume it's do a little bit with the DVL, but I'm not 100% sure.
Yeah, ice is generally not transparent, actually. Like you can get a very thin layer of ice at the surface that is transparent, but the thick ice melt, it shows up. Like one of the problems is how reflective it can be, but the underside of ice tends to actually not be super clean or perfect. It's not like a perfect ice cube from your freezer. So you can actually visually detect ice pretty well, and it shows up very brightly in sonar. And it has a very distinct sonar signature. So I think it's a combination of sensor, multiple sensor modalities, which is a big part of what we're looking at for our work.
Great. Okay, we might. Or do you have a question, Mick? We have 1 minute.
I was just going to ask, I've seen you've done some work in hyperspectral underwater imaging, and was curious how you're seeing it with an ROV, because I noticed at the start you were talking about like algae from thrusters being like churned up and stuff, and how you're dealing with that in your attenuation modeling, and if that's something you're working on or interested in. If that was
Yeah, so that hyperspectral work, I got involved with Jay Zhang, who I've been working with closely here. He's a PhD currently. He was an undergrad when I joined the ACFR, and well, he had just finished undergrad, was just joining his PhD. And so I kind of worked with him to, he had started on that hyperspectral work during his undergrad, and then I helped him kind of take it over the line to a publication. And yeah, that preliminary work, it's kind of a survey method. So you assume that you're standing off of the environment, not disturbing it. And there's also, if you look at the publication, there's kind of two different modalities that we looked at. One is assuming you are illuminating your scene artificially, no ambient light present. The other one is assuming you only have ambient light, no artificial illumination. But it gets really tricky when you get into super rugose terrain, where if it's ambient light and you're looking at a wall, now you get all these shading problems that come in. We have not addressed that. So the simplest problem is artificially lit, where you can model the structure and model your lights and model your camera. And there's also some work that was kind of conducted around the same time by NTNU, Norwegian Technological University, with Oscar Pizarro, who I work with a lot. One of his students put out a really good work on doing a hyperspectral survey with a ROV in deeper ocean water. So there's some ideas about how we want to extend that work, but currently the method that we have published, that's quite constrained to certain operational modalities and doesn't really deal with kicking up turbidity, or degrading your water. But yeah, I don't know if that answers your question.
Awesome. Okay, well, we'll leave it there, but I do just want to thank Gideon again because he's had a lot of field work and deadlines and things, so I really appreciate you taking the time to speak with us. So can we thank him one more time?
Thank you, Skylar.
Cheers.